Okay, thank you. So hi everyone, welcome to this week's seminar. Thanks for coming. If you have any questions throughout the seminar, please ask them at the end, or if you're watching on YouTube, put them in the chat and we can ask them for you. So now I'll hand over to Anthony, who is introducing our speaker for today.
Yeah. Hi everyone. So today we have Lucille Carbillet, who's a PhD student at the Institut Terre et Environnement de Strasbourg. She's working in the experimental geophysics section and under the supervision of Michael. She focuses on subsurface formation processes and failure modes that affect the mechanical behavior of materials in the crust. Her PhD thesis focuses on the evolution of hydraulic and mechanical properties of porous rocks through the granular and non-granular transition. And basically what she's going to be talking about today is the use of synthetic samples to look at this mechanical behavior to understand crust properties. So Lucille, if you're happy to start, you can just share the screen.
Yeah. Okay. So you should be able to see the screen now. So thanks again, thanks a lot for the invitation and the introduction, Anthony. Thanks to the entire Earth Sciences Research Group at Liverpool. It's really nice to be here to talk today, and hopefully we'll be able to have an interesting discussion about the results I'm going to present. I'd like to start by introducing my co-authors, which are also my supervising team for the PhD. So Michael Heap, Fabian Wadsworth, who's actually working in Durham University, and Patrick Bose, also from Strasbourg. So I'll start with something like 4 slides with a more general introduction, maybe for a broader audience, and then I'll go over different results that I obtained doing my PhD as part of my PhD work. And so all of this is about is to solve this question of the link between microstructure and hydromechanical properties. And the specificity of this work, of this PhD, is that I've been working with synthetic porous rocks. So, yeah, okay. So rocks that form the Earth crust can be viewed as heterogeneous materials. That is to say, materials that are composed of domains of different phases. 2 examples of heterogeneous materials are shown in A and B. So in A, you're looking at a system of hard spheres of 2 different sizes. And in B, you're looking at the internal structure of a sandstone, so a natural rock. In our work, we focus on heterogeneous materials like these 2 previous examples, materials for which the microscopic length scale is larger than the molecular dimensions, but smaller than the characteristic length of the macroscopic sample. So this allows us to view the material as a continuum on the microscopic scale, continuum to which microscopic effective properties can be ascribed. So to illustrate this, let's focus on figure C, where we have a schematic of a 2 phases material on the left, with capital L that represents the macroscopic length scale, and a small l that represents the macroscopic length scale, which I'll refer to as microstructure. If capital L is much bigger than a small l, so if the macroscopic length scale is much bigger than the microscopic one, the heterogeneous material can be treated as a homogeneous material with effective properties. So that's how we usually treat natural rocks in experimental studies. And the question then is, what's the relationship between the microstructure of a rock and these microscopic properties? And how are these effective properties mathematically defined? For instance, are effective properties simple mixture rules involving the phase volume fractions? Very often for natural rocks, the answer to this is no. And so that's why many experimental studies have been conducted to understand how the microstructure controls the microscopic behavior of rock. So then the question you might be asking yourself is, why do we care? And so I've chosen to show you two geological examples to illustrate why we need to know how the microstructural attributes of a rock influences their bulk behavior. So on the left, you can see a geological formation, a sandstone, within which we see various bands that cross the formation. These bands are the formation features that develop in response to the stress conditions at the field location. So these bands will likely change, have likely changed the macroscopic behavior of the rock formation. For instance, they might act as barriers to fluid flows. And so we want to know how and why they grow here with these geometrical attributes, and then be able to predict their formation in other geological settings, or maybe monitor their evolution. On the right, there's an example of the importance of understanding the link between microstructure and macroscopic behavior in volcanic settings. In volcanic edifices, like for instance, Merapi volcano, the physical state, so the macroscopic properties such as the porosity of the edifice host rocks is very important, since the ease with which magma can outgas into the rock can dictate, for instance, the explosivity of the volcano. Therefore, we need to know how these host rocks react when exposed to different pressure conditions to monitor the evolution of permeability and then of the explosivity of the volcano. So once again, this can be achieved by studying how the microstructure of the host rock control the bulk behavior. So in this talk, the effective properties I'll be focusing on are the hydraulic and mostly the mechanical properties, namely the rock strength, so how the rock behaves when it is submitted to various pressure conditions. So there is a long history of experimental studies on the influence of microstructure on the hydromechanical behavior of natural rocks. Here are two examples of experimental results of the evolution of strength, here presented as UCS, so uniaxial compressive strength, with porosity, so phi and porosity, which is the proportion of voids in the rock, basically. So overall, in these data from the literature, we see that an increase in rock porosity causes a decrease in the strength of the rock. However, there are differences between the different rock types. We have sedimentary rocks like sandstones and limestones, and volcanic rocks like andesites. So we see differences within in the different rock types, but we also see that the scatter on the compiled experimental data remain quite large. In fact, trends in these plots are complicated by the fact that microstructural parameters other than porosity, such as grain and pore size and shape, their distribution, or maybe a matrix composition, will change very likely together with porosity. So complexities arise from the fact that the influence of microstructural attributes are all interconnected, and that ultimately a fruitful way forward would be to find a method by which they can be deconvolved and then can be studied, each parameter could be studied in isolation. So to do so, several strategies could be considered, and we chose to conduct experiments on precisely controlled synthetic samples, for which we exactly know and can design the microstructural geometries and the porosity. So we just follow a little history. We follow the rationale of previous experimental studies, some of which actually date from before the 50s, the 1950s. And here you have examples of studies from a study from Amosawi in the 80s, and more recently study from Vassar. They both used glass beads as analogues for quartz grains, and Vassar proposed sintered glass beads as suitable analogues for granular crystal rocks, such as sandstones. So we choose to use this viscous sintering method to prepare synthetic samples and to unravel the contribution of microstructural parameters on the mechanical and hydraulic behavior of the rocks. So I'll now move on to a more technical aspect of the work, and namely the physical process of viscous sintering. So, viscous sintering is driven by interfacial tension between the glass beads and the interstitial gas between the grains. Okay, so during viscous sintering, an initial system of viscous droplets, which can have all the same size, or which can have different sizes. This initial system evolves with time through two main stages. The first one is the growth of necks between droplet-droplet pairs that share contact. That was theorized by Frankel in 1945. And then the next stage at lower porosity is the shrinkage and closure of the pores between the droplets. That was theorized by Mackenzie and Shuttleworth in 1949. So the initial system of viscous spherical droplets and interstitial pores evolves into a system of isolated pores within a viscous liquid continuum. So that's to say that the end state is gas in the liquid, and that's the inverse of the starting state, which is liquid in a gas. So we have a topological inversion, and we actually, this process of viscous sintering allows us to reproduce the transition from a granular to a non-granular state, which is also something that happens during diagenesis for sedimentary rocks, for instance. Practically, in order to reach a desired porosity in a desired time for a given grain size of glass beads, we control the temperature of the synthesis, and we also control the time. So the effect of changing the grain size is actually to change the pore size between the grains, the pore size between the grains. Therefore, the ability to tweak the grain size of the starting glass bead population, so at room temperature, allows us to control the pore size distribution independently from the porosity, and then thus deconvolving these structural controls. So practically in the laboratory, when we say that we prepare synthetic samples, we actually go through very simple steps that I'll present to you now. So at room temperature, we can design different types of distributions. We can choose to go to the simplest, the simplest distribution, which is all grains have the same size. So that's what we're going to call monodispersed distribution. Here in A, you have an example of the more monodispersed we went. So that's not actually monodispersed, because we have like a distribution not only with one peak, but that's highly monodispersed. We can also choose to go a little more pore dispersed, and we can also choose to change the modality of the distribution. If we go more pore dispersed but still monomodal, we can prepare this type of distribution. So like widening the grain radius range that we use, and we can also choose to like basically mix beads with one size, like big beads with smaller beads, and that would change the modality of the distribution. And we've been preparing, for instance, bimodal distributions. So I'll use S as the parameter to characterize pore dispersivity. And keep in mind that when S is equal to 1, we're purely monodisperse. And as S decreases up to 0, we go more pore disperse. Okay, so using these distribution at room temperature, we'll then go through different steps and prepare the synthetic samples. So I wanted to do like, can I launch the video? I wanted to show you this in a short video because I think sintering samples in the laboratory is kind of like cooking a cake, and you'll see that the steps are actually quite simple. So at room temperature, we choose our distribution, and then we pour the beads in a tray. Very simply, we put the tray then in an oven, in a furnace that goes to very high temperature, obviously. And then after some time that we've chosen, the sintering time at a certain temperature, we get this sintered block from which we'll be coring cylindrical samples, for which we perfectly know the grain size, the ball size, and also the final porosity. So these samples that we use then in the laboratory usually have the dimensions 20 per 40 millimeters with known microstructural attributes. And we also did a little investigation of their intact microstructure, which you can see on the right here. So on figure D, you have an SEM image of the microstructure of a monomodal sample. So you see all grains have almost the same size here. It's not very sintered. The porosity, the final porosity is quite high here. So you can still see that there is a lot of porosity in black, and the beads are in gray. But we clearly see the necks in between the adjacent grains, and we already can see the pores that would finally be isolated if we would go further in the sintering process. On figure E, you can see the microstructure of a bimodal sample this time. So it's basically the same thing, but like with bigger grains and smaller grains. And again, you can see the necks in between the particles. So with all these samples, we systematically make various measurements of various effective properties. I've chosen here to show you only 2 because we measure a lot more, but that's a lot of data. So here you can see results obtained from measurements of wave velocity presented against porosity. So P wave and S waves. And what we see here is that porosity, the more porous the sample, the lower the wave velocity. And what's really interesting here is that it is clear that for a given porosity, changing the grain size actually doesn't change the wave velocity. So the influence of grain size here on wave velocity is not of the same order as the porosity's influence. And so that's in agreement with Raymer, Hunt, and Gardner from the AT, who predicts the wave velocity using the porosity only. On the right panel, in figure B, you can see results of permeability measurements. So it's presented permeability against porosity, scale porosity. And what we see is that the overall trend is that permeability, as porosity increases, permeability increases too. And we see that our data nicely fits on different lines, which corresponds to different grain size. So here the grain size does make a difference, and the dependency of permeability to porosity is actually very well predicted by this universal scaling proposed by Malthus in 94, and then remodeled by Wadsworth in 2016. So I'll move on now to the aspect of my work that has taken me, I guess, the bigger part of my work, which is studying the mechanical behavior of our synthetic samples. So before I do this, I just want to remind you a little bit of the type of experiments that we do in the laboratory. And all these experiments were conducted on a triaxial apparatus that we have in Strasbourg, on which we basically control independently three different circuits. One circuit is for the confining pressure, so the pressure in the fluid that surrounds the sample. Another one is for the pore pressure, to the pressure in of the fluid inside the rock, which is very often water. And then we also control the axial pressure independently from these two previous, using a metal piston that can be lowered on top of the sample. So we have conducted two main type of experiments, hydrostatic tests and triaxial tests. During the hydrostatic experiments, the confining pressure, so the pressure around the sample, is increased in small steps, while the pore pressure is kept constant at 10 MPa. So the stress state around the sample is such that the stress is the same in all directions. During triaxial tests, we place the sample under hydrostatic condition. So we increase the confining pressure and the pore pressure to targeted values, and then they stay constant as we increase the axial pressure by lowering the piston on top of the sample. So this time the stress around the sample is such that sigma-1 is higher than sigma-2 equals sigma-3. All our experiments were conducted at room temperature on water-saturated sample under drain conditions. And we also recorded the acoustic emissions during the experiment. So just a quick reminder of the terminology I'll be using. I'll be referring to the effective pressure, PF, as which is the difference between the confining pressure and the pore pressure. I'll also be referring to the difference between sigma-1 and sigma-3 as the differential stress Q, and to sigma-1 plus 2 sigma-3 divided by 3 minus pp as the effective mean stress. So our deformation experiments provided us with mechanical data. And in addition to these, we also prepared thin sections from the deformed samples, which were observed under the scanning electron microscope, which provided us with microstructural data. So we have both points of view. And here you can see, so for the next couple of slides, keep in mind that I'm only talking about samples that have a monodispersed grain size distribution. So I'll usually be referring to a mean grain diameter, and keep in mind that all grains in the rock basically have this diameter. So here you see representative data for hydrostatic experiments. These mechanical data are plotted as the effective pressure against the porosity reduction, and in this plot, the hydrostatic curve can be divided into 3 parts. So the first part, nonlinear, corresponds to a deformation by reorganization, rotation of grains when stress is first applied. Then we transition to a stage at which porosity decreases linearly with the effective pressure. And this is the part of deformation that we consider to be the elastic regime. And then as we increase effective pressure further up, we reach a value that is marked as P star. And at the same time, the acoustic emission burst. And we see that the porosity inside the rock, the porosity of the rock decreases suddenly and substantially, while the effective pressure remains actually almost constant. This P-star value is referred to as the critical pressure for the onset of grain crushing. Indeed, if we look into the microstructure of the rock, so that's the experiment that corresponds to these SEM images. We see that within the rock, all grains are completely crushed, and we can see shards of glass in place. So as we reach P-star and the porosity decreases suddenly, all grains in the rocks are completely crushed almost at the same time. And so this is the result of the homogeneity of our samples, and they're so homogeneous. Plus, all grains in the rocks have exactly the same elastic properties. If we look into the mechanical data that we have from Traxel experiments, this is basically what we usually had when we did experiments at high confining pressures. So this time, mechanical data are plotted as the differential stress Q against the axial strain. The first part of the curve corresponds again to the elastic regime of deformation. And once we reach this really subtle change in the slope, and at the same time we see that the acoustic emission burst again, we actually transition to the elastic regime of deformation. So this critical stress is called C-star, and it's the critical pressure for the onset of shear and hence compaction. So as we go beyond C-star, we see that on the mechanical data that the stress strain curve is punctuated by stress drops concomitant with peaks in the AE activity. Usually, these stress drops these are mechanical instabilities that appears when compaction bands or localized deformation features appear in the rock. And indeed, if we look into the microstructure of this sample that was deformed up to 2% of axial strain, we observed bands, cross-cutting bands, horizontally in the horizontal direction of the sample. And so this discrete band is actually a compaction band. So if you remember the first example that I gave, in the geological setting with the sandstone formation, the big bands that we saw were actually also compaction bands. So in our synthetic samples, we actually were able to reproduce or to get the same type of microstructural features than what's been observed both on the field and in the laboratory on natural rocks. So using these mechanical data, for each experiment, hydrostatic and Traxel, every time we did an experiment, we identified these critical stress states. And these critical pressures were then used to map out the failure envelopes for our samples. So failure envelopes are basically allowing us to locate the stresses required for the onset of inelastic deformation. And so depending on where we are on the failure envelope, the failure mode is not the same. So when we're at low effective pressure like this, and we are beyond the elastic envelope, the sample failed by brittle failure, so the development of a microscopic shear fracture. So this type of failure mode, I'm not going to talk a lot about this later on. I'll be focusing more on the failure mode that we see as we go to higher effective pressure, which is shear enhanced compaction. And that's also the stress state at which we have the formation of compaction beds, for instance. Under hydrostatic loading, the sample failed by grain crushing. So we see here that all our experiments were conducted on samples that were that had different grain diameters and different porosity. And in fact, all these experiments were conducted to investigate the influence of these two microstructural attributes, porosity and grain size. And before I discuss the results, these results, I just want to quickly go over, say a few words about the comparability of our data with data obtained on natural sandstones. So in figure A, there's a compilation of results, mechanical data from hydrostatic loading. So it's plotted as the effective pressure against the porosity reduction, and in the color curves are the one obtained on the synthetic samples, while the black curves are the one for natural sandstones. What we see mostly on this plot is that while the transition to grain crushing is very sharp in our synthetic sample, and that's like it's very sudden, and the porosity and all grains get crushed almost at the same time with the rock, it is more progressive for natural rocks. And this is mostly due to the very monodispersed distribution that we used. Focusing on if we compare the result for triaxial compression experiment at high effective pressure, and so you have an example in figure B with the differential stress against the axial strain again. The orange curve is for a synthetic sample, and the black curve is for bent sandstone. So both have very close porosity and very close grain size, and we see that for this close porosity, the mechanical data are actually very similar between our samples and the synthetics and the natural sandstone. And for a very small difference in porosity, the stress required for CSAR is actually not changing by much. So then if we think of what's going on in the microstructure, we also saw that our results are very comparable to what's been observed on natural sandstones. So again, it's a comparison between bentime sandstone and synthetic samples. So you have their distribution in figure C, and in D and E, you can see the compaction band that was a compaction band that was formed in a synthetic sample in D, and a compaction band formed in bentime sandstone in E. We see that in terms of geometry, these compaction beds are very similar. So all these observations made us more confident on the suitability of these synthetic samples as analogues for crystal rocks, and mostly on the similarity of our samples with well-sorted monomineralic sandstones, such as bentime or maybe Fontainebleau sandstone. So we can then discuss the influence of porosity and grain size. So porosity has already long been recognized as a first-order control on mechanical compaction. But we were able to demonstrate that, all else being equal, increasing porosity from 22 to 35 decreases the stress required for the onset of inelastic compaction by more than a factor of 5. Grain size, on the other hand, and which had been considered but less studied and never in a deconvolved way, also exerts a first-order control on compactivity yield. So that's really clear on this figure A, where we have failure envelopes for synthetic samples in colors, And we see that as we increase the grain size of the synthetic sample, the rock like basically gets weaker. And more precisely, as we increase grain size from 0.2 to 1.15, we decrease the stress required for the unsettled inelastic compaction by more than a factor of 2. So this is the first time that we were able to study grain size in a deconvolved manner and to really show that it has a first order control on the mechanical behavior, just as porosity. And so it is important to remind us that grain size should become a routinely measured parameter when dealing with mechanical properties of rocks. So now that I've been focusing on monodispersed distribution for a long time, the question that arises naturally is, what if we get a little bit more pore dispersed? What if we mix grains of different sizes? So that's what we've done. And so the next part of my talk will I'll show you the recent results that we got, but there's a lot more to be done, and so that's just the beginning. So I'll start with changing the distribution by changing its modality. So first, I tried to mix basically big beads with small beads, and so I put here for you to see the different distribution that I prepared and the corresponding microstructure, intact microstructure. So we see that, keep in mind that maybe in green, we have more smaller beads. It's really clear here in the microstructure. The yellow data are for 50-50 between a 50-50 ratio, and the orange part is more bigger beads within the sample. All these samples have quite high porosity, and the reason for this is that we wanted to stay in a space where we can work and map the entire failure envelope, because glass is quite strong. We wanted to be able to work under all the pressure conditions necessary to reach all the different failure modes. So here is like an overview of the data, of some of the data that we got. So in A and B, you can see results from a hydrostatic compression experiment. So again, it's the effective pressure against the porosity reduction. And I've been compiling the results for bimodal samples with the corresponding monomodal end members. So you see, for instance, this is for 112 microns and 261 microns, and that's right in the middle. That's the sample that is 50 and 50. And so what we see on all these results, we see two things. First, it's interesting to see that when we when we deform bimodal samples, they're weaker. The stress required to reach P star is lower than for a monomodal sample. The second observation here is that the transition to inelastic compaction is not as sharp as in monodispersed sample. Indeed, it looks a lot more like the data obtained on natural sandstone, where it's more progressive and there is sometimes a little bit of hardening in the post-yielding behavior. Regarding the behavior under triaxial conditions, we have to look at figure C. So again, that's the differential stress Q against the axial strain. And in that curved, you have the result for monomodal samples, monodispersed samples, in fact, and below them, we have the results obtained for the bimodal samples. Again, the stress required to reach inelastic compaction is much lower in these samples compared to these ones. And what's really interesting here also is that the post-yielding behavior, so after P star, we don't see any stress drops on these curves. while we were seeing them almost all the time on the monomodal samples. So we want to look into the microstructure to see whether these mechanical data have actually, whether we see these deformation features or not. So regarding the hydrostatic experiments, for both type of distributions, we see delocalized deformation with extensive grain crushing in the rocks, and we can't really make a difference between the failure modes between monomodal and bimodal. However, whereas under triaxial conditions, while we were observing compaction bands in the monomodal samples, in the bimodal samples, we don't see compaction bands, we don't see localized deformation features, but what we see is that the strain is concentrated to the smaller grains in between the big grains that will remain intact. Okay, so this is in agreement with what's been discussed before, using natural materials, that homogeneity promotes grain size localization. And so here, these results show this, and we want to go. We want to do a lot more on the side and study how the compaction bands are formed, and maybe if there's like a threshold in pore dispersivity for the formation of these localized features. So I'll now switch to something that is maybe a little less complex, because these bimodal samples are really interesting, but the thing is we're changing two things at the same time here, because we're changing the modality of the distribution, but we're also playing a little bit with the pore dispersivity in itself. So it's really complicated in the previous data to know whether it's a difference in the mean diameter that renders the samples weaker, or if it's due to the type of distribution, the fact that they're bimodal distributions. So we wanted to work with monomodal samples, but a little more pore dispersed. And so we prepared more pore dispersed monomodal distributions. So that's the pink distribution here that corresponds to the pink envelope in figure A. And I've put the corresponding monomodal monodispersed distribution. So by corresponding, I mean with the same mean diameter in green on the same plot here. And so that's the green envelope here. While you're looking at this, keep in mind that all these samples are the same apart from except for their grain size distribution. So we're really studying grain size distribution in isolation here. And so these are just very recent results, and the beginning of our current project. But what's really interesting here is that we don't really see a difference in strength under triaxial condition, but when we deformed the samples under hydrostatic conditions, we see that there is actually a big difference in the stress required to reach grain crushing, so the P star. And what's really interesting is that this observation was previously made on natural rocks, and this is something that was shown by Cheng and Al in 2012 using Boise and Burrisviller sandstones. So these two sandstones, just as our synthetic samples, have the same porosity and almost the same mean grain diameter, but they have different grain size distribution. And what is really interesting is that they also see that under triaxial condition, there's not much difference in the strength of the rocks, the sandstones. But as we deform the sample under hydrostatic loading, P star is reduced as the distribution gets wider. So what we can say maybe is that it seems that pore dispersivity might have a different impact depending on strength, depending on the failure modes yeah. So that's something, if you have a question about this, I'll be really happy to talk about this a lot more. But I'm going to stop here and go through different take-home points because there is lots of data and there's a lot more to be done using these samples because I think we showed with these studies that sintered glass beads are highly suitable as analogues for crystal rocks, such as sandstones. And I've not been mentioning this a lot, but toughs do. So there is broad implications and applications of the results, both in sedimentary settings and volcanic settings. For instance, hydrocarbon geothermal reservoir and subsidence, or volcanic edifice instability and spreading. Using the mono-dispersed samples, we were able to demonstrate that both porosity and grain size exert a first-order control on the mechanical compaction of synthetic rock. And so alongside porosity, grain size should become a routinely measured structural parameter. Then using the more dispersed samples, we were able to see that the type of grain size distribution, both so modality, bimodal, monomodal, strongly influences the compressive strength and the propensity for compaction localization. And finally, we also saw that pore dispersivity exerts a complex but significant influence on the mechanical behavior and the failure mode of the synthetic rocks. So finally, I think there is obviously a lot more to be done using these samples, but that they opens up new perspective for the study of the relationship between microstructure and microscopic behavior of porous crystal rocks. On this, if you want to read a little bit more about this, mostly on the mono-dispersed samples, we published a paper about that in 2021, and I thank you for your attention, and I'll be pleased to answer some questions if there are any.
Brilliant, thanks, Lucille. Do we have any questions? Yeah, Janine?
Hi, Lucille. That was a really interesting talk. I wondered, so the experiments, they're very idealized compared to nature. And so I just wondered your thoughts on sort of for the next steps in the experiments. What would be the next level of complexity that you would choose to introduce? And then also, what is going to be like the most difficult part of nature to try and replicate in these sort of experiments? Does that make sense?
Yeah, it does. So that's really interesting. I think what's exciting about these samples is for sure we started like with the simplest that we could do, and every time we talk about this project, we have loads of people asking for maybe cement or all sorts of parameters that we could study. So I think the pore dispersed part is actually quite complicated. So I haven't presenting it, but the preparation procedure for the bimodal samples is actually a bit different from the monomodal samples, because I wanted to be sure that I know exactly the grain size distribution inside my sample. So I could not prepare blocks, because if I were to prepare blocks, I wouldn't be sure that the distribution in my sample was the one I prepared in the block, obviously. So I had to prepare the samples as individuals. So that's one very, like, that's the technical issue that is actually hard to solve, in fact. And so I think the polysphere thing is already a lot, and might be, I think the results that I have so far are, I don't know, are give us like a feeling that there might be something under to be studied there. Like for instance, for the compaction localization, it's really interesting that we don't have them at all on the bimodal samples, in the bimodal samples. And I've been wanting to prepare maybe a suite of samples with different pore dispersivity and just run, you know, exactly the same tracks for tests and see when we stop having these deformation features. Mm-hmm. But then I guess cement is also like the golden, like something that many people are interested in. Another thing we could consider is for sure the, I've lost the word right now, but with beddings and anisotropy.
Right.
I think we could also think of a project for studying anisotropy using these samples, I think. And that might be quite complicated too.
Yeah, no, it's really interesting. Thanks for your talk.
Thank you.
Do we have any other questions? Okay, so I think then I do have one. Okay, thank you.
Thanks for a really interesting talk. I was just wondering if you had investigated the effect of the pore water pressure, and or if this would have a big influence.
That's a good question. I have not studied this at all. I haven't even considered it, to be honest. But so I wonder what might happen. I'm not sure what difference it will make, actually.
Okay. And also, I had a second question. You just mentioned the shear fracture that you weren't focusing on that. Is that like a focus of a different study?
So we started working, so the UCS, the uniaxial strength of these samples is also something that we've measured, in fact. And so I haven't showed the data, but I think I've got them, yeah, right there, in fact. So we've measured the UCS of the samples, and that's not the entire data set. I've measured more since then, but what's really interesting with the uniaxial strength is that we see, so the overall trend is the same, but it looks like the pore emanating crack model that we usually use to predict the slope and the trend in the UCS against porosity is not the right one for these data and fails at predicting the UCS using the porosity. In fact, we realized that there might be a change in the micromechanism for failure at some threshold porosity, maybe over there. So that's something we're currently working on, and I'm waiting on thin sections to see the sort of like, so what do we see as the failure mechanism? Do we see earthen cracks, or do we see grain crushing sort of thing? And then we might be able to say a little more. But then on this part, I'm not sure how not comparable to natural rocks that would get. So that's always, you know, the limits of this work.
Okay, thanks. It's exciting to see what happens.
Yeah.
Okay, and then we have John.
Hello, John
Hello. I can't hear you well.
Okay. Well, let me ask. I believe that there is some maths behind the grain size effect on stress systems. Now, I'm not an expert on this, but I know that the phrase Hertzian contact comes into it, and I think that Ernie Rutter once explained to me the grain size effect. But basically, I'm asking you, have you explored the mathematical framework that might assist in interpreting your result?
Yeah, so I've been looking into it. I've started to look into it because this is an ongoing work. And so I was first surprised by using the different sizes and the bimodal samples. I was actually expecting to have something that is stronger, because in the numerical simulations that were conducted recently, mixing different changing the distributions, they actually predict that if we mix different sizes and if we add smaller grains to an ensemble of big grains, we would actually make the rock stronger. So that's the reason why I was skeptical first about these data. So I think there's definitely something to be done with the mathematical aspect of the question to explain why we get these data. The reason why I still consider our data to be not okay, to be correct, is that microstructurally speaking, what we see, the small grains that are crushed between the big grains, is actually what we saw on natural rocks and what we would expect. So I think there's but there's definitely something to be done with the mathematical aspect of this question of the influence of grain size. Definitely.
Very interesting. Okay, so your picture, I remember it vividly. I mean, it was very clear that the small grains were shattered and the big grains weren't. It was very convincing. Of course, it's an experiment. It does what it wants to do. But I think what you've drawn attention to there is, it's not just that there isn't a mathematical model. There is a mathematical model, but it's predicting the opposite to what you're seeing, which is very interesting. Thank you.
Yeah, exactly.
Thank you.
Thank you very much.
Okay, cool. Well, I think we are just out of time, so we'll leave Lucille for bringing questions. If we have questions on YouTube or more questions, you can probably just either email or Lucille, if you can check the YouTube channel.
Absolutely.
Otherwise, email Lucille if you have more questions about her work. Thank you, Lucille.
Thanks a lot.
Thanks, Lucille, for a great talk. This was excellent.
Thank you very much.